Hi, it is time for day 21 of Advent of Code 2022. Yes, I am wearing the same clothes as the video for day 20. That's because I recorded that like half an hour ago. So that's it. Day 21 was not too hard. There were a couple of minor details that tripped me up a little bit, caused me some delay. But mostly it was relatively straightforward. But let's take a look and dive right in. Okay. Boop. Day 21, Monkey Math. The monkeys are back. You are worried that they're going to try to steal your stuff again, but it seems like they're just holding their ground and making various monkey noises at you. Eventually, one of the elephants realizes you don't speak monkey and comes over to interpret. As it turns out, they overheard you talking about trying to find the grove. They can show you a shortcut if you answer their riddle. Each monkey is given a job, either to yell a specific number or to yell the result of a math operation. These are very smart monkeys. All of the number yelling monkeys know their number from the start. However, the math operation monkeys need to wait for the other two monkeys to yell a number, and then those two other monkeys might also be waiting for other monkeys. Your job is to work out the number the monkey named Root will yell before the monkeys figure it out themselves. For example, we have a list of, 15-ish monkeys here. One called Root, one called Thol, one called Zzz, and one, you get the idea. And Root needs the value from PPPW, which is here, which in turn needs CCZH, which is up here, and so on and so on. So, yep, that's kind of what the data looks like. Each line contains the name of a monkey, a colon, and then the job of that monkey. A low number means that the monkey's job is simply to yell that number. A job like AAA plus BBBB means the monkey waits for the monkeys AAA and BBBB to yell each of their numbers. The monkey then yells the sum of those two numbers. Similarly, for minus, the monkey would yell this monkey's number minus this monkey's number, and you can multiply and you can do division as well. So in the above example, monkey DRZM has to wait for monkeys HMDT and so on and so on. And then fortunately, fortunately, both HMDT and ZCZC have jobs that involve simply yelling a single number, so they do this immediately, 32 and 2. And then monkey DOZM can then yell its number by finding 32 minus 2, which is 30. And then, yeah, blah, 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 blah. And eventually it will shout 150. So this process continues until Root yells a number, which is 152. However, your actual situation involves considerably more monkeys. And what number will the monkey named Root yell? All right, so yes, indeed you do. It is significantly more elaborate with the real input. I don't remember exactly how many there were, like, yeah, a lot. But that will not deter us. So let's take a look. Let's take a look at the input first. There are 2193 monkeys in our pack. So what I was thinking here was, because there are so many monkeys, I didn't want to do this recursively. I thought that was, I figured that either that would be a problem on the first run through, or it would become a problem in part B, depending on what that turned out to be. So I didn't want to use a recursive function for this. So instead, I came up with this little gem here. So as usual, we get the lines from the file, and then we parse them, which gives us a set of knowns and a set of unknowns. Let's take a look at the parse lines function. That's that will probably explain a lot. So once again, let's split this right so we can see it. Don't need that. Okay. So we start by defining a couple of empty dictionaries, knowns and unknowns, and then we go through each line over here, split by the colon, which gives us the key, or the name of the monkey, and an expression. And if every character in the expression is a number, then we treat it as a number and we store it as a float. I had originally made these integers, but it turns out that is not going to work. We need a little more precision than that. Not exactly like floating point, but more than no decimal, more than no decimals after after the decimal point, obviously. And if they are not all numbers, then we store the string simply as the expression just as a string in the unknowns dictionary. So knowns is all the values that we currently know, and unknowns are the values that we have yet to work out. So that is what we do here. We have a while true loop, and we keep going through it. So we keep evaluating, we keep looking at elements in unknowns, and we split that up into the first argument and the second argument and the operation between them. And we check if the two arguments are known, and if they are not, we go through, we continue to the next element in unknowns and try to keep doing this. If they are known, then we get the numerical values of them, and we use Python's eval function to evaluate the expression, replacing the values or the names of the names of the monkeys with their corresponding values with the operation between them. And once we find that, we call break, and we delete that name from the unknowns list, because now it is known and we can use it for subsequent computations. And then we start over. So going through unknowns until we find something that, something we can do, delete it, and keep going through until at some point root's value is known, and then we return the known value. And that's it. For the test input, we get 152, which was what we wanted. Yep. And for our own input, we get this much, much larger number. And even though this could potentially, have a lot of iterations, it's going to be more efficient than trying to do this recursively. And it's, it's pretty performant. So that is basically part A. All right, let's take a look at part B. Due to some kind of monkey-elephant-human mistranslation, shocking, you seem to have misunderstood a few key details about the riddle. First, you got the wrong job for the monkey named Root. Specifically, you got the wrong math operation. The correct operation for monkey Root should be equals, which means that it still listens for two numbers from the same two monkeys as before, but now checks that the two numbers match. Second, you got the wrong monkey for the job starting with hum. It isn't the monkey, it is you. It is the human. Actually, you got the job wrong too. You need to figure out what number you need to yell so that Root's equality check passes. The number that appears after yum in your input is now irrelevant. In the example above, The number you need to yell to pass root's equality test is 301, and this causes root to get the same number, 150, from both of its monkeys. So what number do you need to yell to pass root's equality test? All right. So what I decided to do here was, let's take a look at part B. So once again, I get the knowns and unknowns, using the same function as before. And then I create a function called try guess, in part because solving part A, revealed that this is very fast. These are very fast operations. So just trying a guess by starting from scratch, it was perfectly reasonable. So I pass in knowns and unknowns, create copies of them. I change the human's value to whatever we're guessing. And then we go through pretty much like in part A, except we special case the situation where we've made it to the root monkey and we know both the values that are coming in. Instead of doing the, what the description said, which was to, basically return a Boolean, it's going to say yes or no, or true or false, whatever, right? We return the difference between them because that helps us narrow in on finding the right solution instead of just, nope, that didn't work, and then we wouldn't know what to try instead. Let's see, that is pretty much it. So yeah, this is not exactly like it is up here, not for any particular reason. That's just how it happened when I was copy and pasting a little bit and then cleaning up after. Okay. And then I use something called Newton's approximation method, which uses so you have a guess. This is not exactly Newton's approximation method because Newton's approximation method requires you to differentiate and stuff. So that's not what we're doing here. We basically start out by, some start number. In our case, that is 0. Just for we have to start somewhere. And then we set a dx to 1, also just to have a starting point. Yep, so we start by trying 0, and then we tee up the for loop, or the loop here with a new guess, which is the previous guess plus some dx value that we are also just guessing. And then basically we keep going until we find the result. And the way that we try to pinpoint it is we try the guess, we get the new result, and on the first go through, the current guess is going to be 1 more than the previous guess. If that gives us the right answer, new result is try guess, which gives us the difference between the two the two monkeys that root has to look at. And if that is the goal that we wanted, which is 0, then we're done and we return the value. Otherwise, we calculate our new dx using this little gem here. So we take the current guess minus the previous guess, and then we multiply that by the new result, so what we got now, divided by the difference between the previous result and the new result. So what that tells us is if moving 1 in a direction Sorry, let me think about how to explain this. Yeah, so basically what this does, if you can see that moving whatever distance you moved, your previous guess and your current guess, if moving that far got you, say, a tenth of the way to the right result, then we just extend the guess to in that same direction. So you can kind of think of it as, it's somewhere, the result is some kind of graph, right? And then you can think of it as using the derivative to find the direction to go in and approximately how far. And then the idea is we try again, because we don't just assume that that's going to work out perfectly. So we try, so we get that result, we calculate the actual value, and and then we try to eventually zero in and find the final result. And that's what we do here. And because this is a reasonably well-behaved function, this only takes, I think, 2 iterations each time. So that is pretty handy. And you can see that gives us an answer pretty quickly. For some reason, my biggest challenge in this one was realizing that these don't have to be integers. And for a while, I was turning everything into integers, and I got real confused because I got a result from my part B, and I put it in, and it wasn't right. It said it was too high, and I couldn't figure it out, because all the calculations worked. I tried changing the input and running part B again. No, sorry, part A again. I changed the input file, put in the value that that my part B spat out, and said this is supposed to be right. And it was right. I got the right answer. And then I realized that I got the exact same answer if I subtracted 1 or added 1 or maybe even 2 in each direction. And it was like, okay, so which answer is the right one? And it turns out that apparently the first one is the right one. And why, right? That wasn't part of the description, that if there are multiple correct answers, I want the lowest one. It turns out that if you treat them all as floats, so you don't assume that they're integers, then you get a unambiguous answer. And so that was the final trick that I needed, which cost me easily 20 minutes. A little annoying, but here we are. But that was day 21. I hope this was helpful. And if you have any questions or comments, you leave them below. Otherwise, like and subscribe, and I will see you tomorrow. Bye.